Alright, so this video we talk summation. And there's really two ways you can tell people about it. You can say, oh, it's this. You know, clearly it's just adding numbers. And then to some, capital. If you show someone this, they're like, if this was the brain, that's the brainstem, I guess, whatever. Very sloppy. But you get the idea. If this was their brain, this is what I'd do. If this was its switch, imagine a switch if you can. Very difficult. But this is on, this is off. Well, it went from here to here just as soon as you search on this, because it's meaningless without some knowledge of where it comes from. Either way, this letter is called sigma. Well, either way, the other way you could do it makes people feel dumb. And it's saying, oh, it's just adding. Just adding. And you know how to add, right? Like, just adding. And then so no one will want to learn it, because if it's just adding, just addition, then that's boring and I don't need to relearn it. Waste of time. But before we get into it, let's not even bring all this stuff up. Let's bring up a famous problem. And this is the problem. I mean, the famous, I don't know, it's kind of a fun problem. What's 1 plus 2 plus 3 plus 4 plus, keep adding, plus 98 plus 99 plus 100. What is this equal to? Well, there's one method that you're probably going to try, and it's going to take you forever. And that is 1 plus 2. So that 3, 6. 6 plus 4 is 10. 10 plus 5 is 15. 15 plus 6 is 21. Either way, that's going to take you forever. We got to 6, and I'm starting to have trouble in my head. And, I mean, you could do this, but there's a better way. And this story goes back to a mathematician named Gauss. This story may not be true, as he was a boy when this apparently happened. But so we know a little. But so Gauss was given this problem. Carl Friedrich Gauss. This is a German mathematician during, I believe he was born 1780. I'm gonna throw that year out. Yeah, let's say about 1780 to I'm really guessing here. I could look this up in a second. To about 1850. That's my guess. So anyway, this is the problem. I'm gonna leave it here for a second. You try to solve it while I try to figure out the year Gauss was born and I guess died. Anyway, great mathematician. So Gauss had, so there's two mathematicians that are my all-time favorites, and it's Euler and Gauss. And Gauss was a mathematician that is exactly what you'd expect. Kind of hard to understand idea-wise, and he kind of believed in this having a diamond at the end of your process, and that's just how it works. You just work through mathematics until you get a beautiful answer, and that's the point of it. Whereas Euler, my actual favorite mathematician, he's all about making sense and giving true proofs and really just playing around with mathematics, and I prefer his approach. But either way, all right, so I found it. So his actual year of birth was, I was close, 1777. 777. And his actual year of death is 18. I was very close. 1855. There you go. Ignore this stuff. All right. Yeah. Anyway, so there's a way to solve this that simplifies things, but we're not gonna get into that. We want a way to write out addition in a useful way. So I'm gonna go writing addition in a useful way. Meanwhile, you can continue work on that, whatever your choice. So let's try to represent some stuff. So here is the first thing to represent. 1 plus 2 plus 3 plus 4 plus 5. Got it? And that's the first thing I want to represent with some symbols. And it might have to do with this later on, but honestly, do whatever. I don't really care. You could make up, I recommend like doing like a bass clef somewhere along the line and factoring that in, because it's music notation, it's not math notation, but you might be able to find a way for it to work. So find a way to write this up. And then after you do that one, use the same method to write up, to simplify this series of numbers. And let's make it, I want something that's similar, like 5 numbers. Let's do like 2, 4, 6, 8, 10. Bunch of even numbers. I want a way to write that up. Last one I want to write up, let's make it a little difficult. Let's do like descending 18 plus 9 plus 0 minus 9. We're going down by 9s. Minus 18. And I'll tell you right now, all of these are called series. So I'll write this out with bass clef. You can use like lowercase sigma if you want. You could use, honestly, I don't really care. Phi, whatever. Lowercase phi, yes. Just use something and look for alternatives. So I would pause it right here if I were you. Try to come up with ways to do this. But I'll actually write up this way with a bass clef. In 5, 4, 3, 2, 1. Alright, let's use bass clef notation. So bass clef equals this. And what do I mean by notation real fast? Notation just means it's basically a way to write up an idea in mathematics. And we require notation for everything we do. And like plus sign is notation, numbers are notation, equal is notation. It's all notation, but it's meaningful notation. And so we want the same thing to represent series of addition. In fact, it's literally called a series. So anyway, so what's something similar with all these? There's 5 numbers. I agree with that. So let's put 5 on top, sure. And somewhere on this symbol we want a 5 to know that we have 5 things we're adding. What's another similarity? Well, it follows a pattern, so there should be a way to put a pattern here to follow. I just need to write up the pattern somehow. And in a sense, this pattern, you could like plug in 1 for the first number. So let's start at 1. Now, how do we know we're plugging in 1? Like, how do we define a pattern? Well, this one, it's just, I don't know, like, so if you know function notation, functions, you put in an input right here, then you have an output, that's the result, the function of that input. So we're basically going to set up a function to go inside of here. So the first function, let's plug in, so let's do these all from 1 to 5, 1 to 5, add numbers 1 to 5. Except for the first function, we're going to add, it's going to be like x. Because if you plug in, that's going to be literally our function. We just make the x value equal to the y value. This is technically the y value in some senses. Or technically make it exactly equal to the x value. Because that would make f of 1, plug in 1 into this equation, you get 1. Wow. F of 2, whatever. You get 2. So anyway, that will be our first equation, just x. And that works. Plug in 1, you get 1. Plug in 2. So you increase it by 1. So that's, yeah, let's say like a plus 1 here. And yeah, all of these you're increasing by 1 on the function. Now this function is a little different. Let's call it like g of x. Just a simple way to arbitrarily write any input thing. And let's make it's just 2 times each number. 2 times each one of these. So I'll make the function 2x. And so the first time we plug in 1. 1 times 2 is 2. Then you add that to the next result, increase by 1. So 2. 2 times 2 is 4. Keep doing this until you get 2 times 5, which is 10. So it works. Nice. And then the last one, I think this one's hardest, but you can still do a function for it. So let's make it like H, F, G, H, alphabet. So if this number is 1, it's kind of like 9. Oh, so why am I writing there? So x would be here. So it's 9 times the number. I know that. So 9 times x. So 9 times 1 is 9. So we have to add 18 to that. Is that good enough? Here, let's make it negative because we're decreasing. We're subtracting another 9 each time. So plug in 1 here, you get 9. So that works. So we need to add another 9 to this. So let's retry this. H of x equals, that's a bad h. H of x. So let's see. Let's think this here. So yeah, we got that negative 9x. So plug in 1, you get negative 9. So you have to add that to 27. There's our function. Yeah, I think that's right. So negative 9x is going to be crowded plus 27. So let's plug in here. So plug in 1. 1 times negative 9 is negative 9. And negative 9 plus 27 is equal to 18. Yep, works. Next one. Increase by 1. So 2. 2 times negative 9 is negative 18. Plus 27. Well, that's just another 9 subtracted from this, so it's 9. And yeah, you keep doing this. Subtract another 9, you get 0. Subtract another 9, you get negative 9. And negative 18. So this works, and you do it until 5. Alright, so that's nice and all. We're not here yet. That's going to take us another sec. So you get the concept here. We're going to write it the math way now with the sigma. And that's just the normal way we write these out. Alright, let's change colors here. Just some variety. Alright, so this is how you'd represent this in math notation. Let's use x to start out, just so you're not going to get surprised or anything. So if you're representing the first thing, 1 plus 2 plus 3 plus 4 plus 5, this is how you do it. You start with 1, x equals 1, and this symbol just tells you from the get-go. You're going to increase this number by 1 until it's greater than this number, which we'll put 5 on top. So what this means, plug in 1. Yeah, just 1. Plug in 2, plug in 3, plug in 4, plug in 5. And now, would we plug in 6? No, 6 is greater than 5, so we stop. So red stop sign. Because 6 is greater than 5. That's basically the idea. Here, let's not even go back to these because I think you get the idea. Those are the function. You just plug that into the same setup. Now, we're going to do it a little differently. And usually we start from 1. You can start it from 0. That's a common one. You can even start from other numbers. This thing would have been simpler if we had started from like negative 2, then like increased it. Because negative 2 times 9 would be, times negative 9 would be 18 already. Then negative 1 times negative 9 is 9, yeah, then 0, yeah. Either way, so you can start from negative 2, and it simplifies problems. The other problem is that there are certain formulas for solving these that makes it simple. We'll discover one of those formulas that will help us solve this. So how would you write that? Before we even get to that above one, let's set up something a little harder, like x squared. Squared numbers, so just add numbers that are squared. Let's multiply by 3 just to make it look even harder. X equals 1. And bring it to, let's bring it to 7, sure. So that's 3 times 1 squared, which is 3. Then 3 times 2 squared, which is 4. 4 times 3 is 12. Then 9, well, yeah, so 9 times 3, that's 27. We got the result earlier. And so forth. You keep adding in, plug in, and the last number you'd add is 7 squared, 49 times 3. I don't want to calculate that. 3 times 50 is 150, so you subtract 3 from that. So it would be 147, I believe. Maybe wrong, but I don't care too much about accuracy here. Anyway, so that's the idea there. And switch colors. So yeah, I like that. The 100, this whole method of adding, because it simplifies problems. There's 7 items here, yet can be represented by this simple thing. And then you can represent 100 items. So let's do that. And by the way, there's a pattern for x squared and stuff that we'll go into in the next video. But either way, we just want a formula for x. Plug in x. Oh, you can also do multiplication, because multiplication is just a repeat addition. So let's make this 6, because we already did 5 and 7. Why not? X equals 1. So this is technically a function. It's just a function that's always equal to 5. So plug in 5, plug in 1, you all still get 5. And then you get 5, then you get 5, then you get 5. That's the 4th time. That's the 5th time. That's the 6th time. And now you have 7. 7 is greater than 5. Therefore, you stop. Oh, greater than 6, I mean. 7 is greater than 6. So you don't continue past that. And this is the same thing as 5 times 7. So there's a formula here. Let's make it letters so we can be completely arbitrary and plug in whatever we want. If x equals 1, and we start with x. Oh, wait, no, we start with any number, let's say a. Just represents any number, a. And we do it to n number of times. The result is a times n. That's a really useful result. And also, we'll prove other formulas in the other video, but that's one formula. Now, next formula, we want to simplify this. So this just is x, and this can be n. So add to n. X to n. And return x equals 1. Alright, so this means add 1 plus 2 plus 3, whatever, keep going, till you add n. And that's when you end. Cool. Alright, so we need a formula for this, though, because writing this out, it's good, but it still comes across this problem. There should be a formula for this. And guess what? We're actually going to solve this problem. And let's do that on this 3rd page here. I would move on to another video here, but why would I leave you hanging on this problem? Alright, so let's write this out. So we have 1 plus 2 plus 3 plus, keep going, then 98 plus 99 plus 100. So this is considered the way Gauss proved it. May have proved it. You can question whether this is factual, but it's still, the proof is actually interesting. So rather than just adding head-on or backwards or anything like that, we're going to add opposite sides. And the reason why, you'll see in a quick second. Alright, so let's start by adding these two. What's 100 plus 1? 1 plus 100? That is 100 plus 1. Alright, let's add that to the next row. What's 2 plus 99? 101. Wow. What's 3 plus 98? 101. Okay. Then you just keep on continuing. Then you get to 50 plus 51, which is in the middle, which is 101. Still, wow. Wow. And how many of these do we have? We have, well, this equal that result. So we have 101, but we're grouping pairs of 2. So we're basically splitting this addition in half. And so we have 100 items here, because we're adding 200, and it's half of that. So 100 divided by 2. And that looks weird for some reason. All right. So 100 divided by 2 is 50. 50 times 101. I'll tell you this now. 50. And we found the result super fast. We didn't do any of that crazy stuff. We just knew there's 50 of 101s. And so that simplified the problem, and we're already done. And I'm going to go into the next video to prove the formula that can solve this even faster than looking at it in this manner. And by the way we represent this, just sort of fast, 100, start from 1, and increase by 1 each time. Alright, and that equals that thing above. And it equals 50, 50. So there has to be a formula that connects anything that has this set up to this. And so we'll do that in the next video. Thanks for watching.